All right, we're off and running. Okay, so again, as I mentioned before, the idea of this talk was after Biplov and I had gotten back from Geo for Good, we wanted to try and make a bit of a summary or just our own impressions of the TensorFlow work that was presented. There was one dedicated 1 hour session on the first day, and there's a lot of content. So we've had a little bit of time to sort of mine through that, and we wanted to give our impressions and also sort of arm everybody so that way they're ready to use some of the new things that are coming out, and use it as a tool for this upcoming year. So we've titled this thing as a sit and learn, but really it's meant to be sort of an active dialogue of if you've got questions on some of the content. We're also learning it as we go. It's a very long notebook, so we'll probably only make it exactly halfway. But I think the first part of the notebook is probably the most important part. It's the newest. It's most different than the past iterations. So let's just get rolling into it. So for reference, if anyone wants to know more about that dedicated session that I mentioned on the first day, there's Google Slides that were put together. I think there's like 120 slides in there, and they literally went through 120 slides in that hour. So it was like rapid fire. Then there's also the recording, which you could watch in tandem, and I would probably recommend that. So if we go through today, you have the Colab notebook. You can use this as a tool, sort of us distilling it. And then you can also come back to these resources that even go even higher level of what is deep learning, how does it fit into the landscape of machine learning and AI, et cetera. They kind of try and start really, really basic and then go very fast. So again, it was meant at Geo for Good to be an entry point, but I think we can start a little bit further down the track. Biplov, do you have anything to say about this slide or your impressions on Geo for Good on the session?
Nothing much. I think there are a lot of changes that's coming in the way we do things. As Nick mentioned in the session, most of the way we're doing previously should work, but that probably won't work in a longer time frame. So this is the right time to learn about this stuff and go forward with it.
Yeah, agreed. Okay, so just move forward. So if you don't have the collab yet, I think everyone, I don't think anyone else joined since then, so everyone should have it. Oh, there's John. Perfect timing. I'll reshare it. Hey, John, let me share this collab with you. It's going to be in the chat for you. So this was one of the collabs. There's multiple collabs in that slide deck that was presented at the session. This one we thought was the best to sort of go through. It's a little less hand-holding and a little bit more in the weeds, and I think that's probably where we want to spend a little bit of time. So when you open up this collab, just save it to your own drive so you've got a copy of it. And you can sort of just quickly start running through it. Most of it runs pretty fast. We wanted to sort of break down the individual components of what's happening, so that way you can get a sense of how we used to do it and how everything has kind of changed now. Move forward here. Oops. There we go. Biplov, do you want to talk about the data processing pipeline?
Yeah, so this is sort of the entire end-to-end workflow. This includes many of the Google product as well as some of the open source product in here. So today we'll mostly focus on this first box, which is sort of a data processing pipeline, and we'll see like how we can use the Apache Beam, which is sort of the framework that we'll be using to do the processing in scale. Once we have, so the output from this data processing pipeline would be a TensorFlow records for training and testing that goes into the subsequent model development. That's basically doing in the second box where you can bake in your own custom model, or you can use one of the standard model. Then you'll be using Vertex AI. What Tim, do you remember the last product that we were using?
It's AI platform,
Yeah.
but I think that's baked into Vertex AI now.
Yeah, so now they recommend using Vertex AI. And then we'll also be using storage and Google storage to store those files. There's a lot of functionality in the Cloud Run, which will not go in here today. Maybe we'll have a separate session next time. In Cloud Run, you can actually operationalize your model. And for example, if there is a new data set coming in, you could have your Cloud Run have a cron job in a way that it grabs the new data whenever it's available, runs the model, and provide those output to the Earth Engine. Yeah, I guess so. For today, we'll just be focusing on the processing pipeline, and we'll see how to do those processing in scale.
Yeah, and for reference, for everyone who's sort of the veteran of this group, who've been here for a long time, the data flow, the Vertex AI, and the Cloud Run are all the new components, and we had kind of talked about maybe doing sit and learn for each one of those as we sort of explore them. The Vertex AI is not vastly different than before, but the data flow and Cloud Run are. And I think at least an hour-long session on the data flow is something that we thought would be really important to get everyone prepared. So that's that. Let me scoot forward. Okay, so then Apache Beam. Let's just kind of go around because this is meant to be sort of interactive. Has anyone ever heard or used Apache Beam in the past? No, yeah, no.
Yeah, I've heard of it.
You've heard of it? Okay.
I saw an early rendition of this notebook and was gonna try and learn it, and then I didn't.
Yeah. From our early sort of digging on it, I think it was a funded project from Google that is essentially a distributed platform. So that way, if you've got a job, you're creating this pipeline and allowing for more efficient distribution of all of your tasks. So it's kind of like Dask, but it's really sort of a platform that creates this pipeline. And what we saw is it's like started in 2019, something like that, as there's funding for this specific development. And it seems as though this is going to be sort of what maybe the main worker for this data flow. So in the code itself, this is probably the endpoint we'll be talking about of how you do all the prep to eventually kick off everything to run in Apache Beam, so that way it parallelizes everything. And I think the big thing here I would mention is that if you approach it, obviously we haven't done this. We don't have example use cases yet. We're not able to say, oh, this works wonderful for illegal gold mining in an operational sense. But just looking at it right now, I would imagine this is going to make scaling things very, very easy because you could just expand to a new location and add it to the batch of regions and just keep your training going. So in that sense, it could be very easy to scale things. The downside there also is, if you aren't doing it correctly, you could incur massive costs. So one thing to be cautious about, and I think also, something more on like the system administrative side, like developing good rigor in like the cloud storage and the cloud run itself. So that way you're not doing these huge jobs that don't need to be done. So those are the two things I think are really important. Biplov, do you have any more thoughts on Apache Beam?
No, I think you covered it all.
Yeah, and the last thing I'll mention is, there's a lot of specific functionality in this package that we just started to tap into. I think, in this example, there's only a few like commands that are actually being used. But I think there's probably you could probably get further and further into the weeds on how to best utilize it. And the documentation is pretty robust from what we looked at thus far. There's both implementations in Python and in Java, but I mean, it would make most sense in Python as of right now, just because we're doing everything in CodeLab. So just putting that out there that it might be something to sort of dig into. If you've got a specific case, there's something that's probably already built in this as well. Let's move on to the next slide. Okay, so this is a very busy graphic here, but we wanted to give you like a full snapshot of what's happening in this collab at 5 different steps. So we've got regions, sample points, patches, serialization, and splitting. Those are like 5 distinct actions, functions that are happening in the script. And the number 1 there represents a specific region. So it's happening at a given region. All of these steps are happening, and then it moves to 2, 3, 4, all of them to produce this batched version of all of your training, your sample points, your patches, the actual serialization, your splitting of data, and then your TensorFlow record. So in theory, this collab is going to walk through each of those steps. And this is the big picture, and we're going to go into it a little bit more detail. Biplov, do you have any more impressions on this as well?
Yeah, so as Tim mentioned, this is sort of the overall workflow for our data pipeline. If you are familiar with the entity relationship diagram on the right side, those curved lines shows what kind of relationship it has. So if you have like multiple training regions that you're trying to generate your data, for example, if let's consider you're trying to generate a land cover map, you probably want to have stratified sample points for each of your classes, right? So that's sort of the relationship it's showing. So it's one to many relationship between region and sample points. That's sort of depicted by that curved line, and each of these sample points are then converted into a patch, because again, it depends on what kind of machine learning framework that you're using. We got this example from Nick's slide where he was trying to use the FCNN, which takes the region as an input, a patch as an input, instead of just points. So that's sort of the third step, where each of these sample points are then patched into a 256 by 256 neighborhood, or whatever neighborhood you want to use. And because these are the floating point patches, right? So it sort of takes more space and memory to process them. So we serialize them into a binary string that's sort of done in the fourth step. And then we divide our training points into our sample points into training and testing. So that's sort of the entire workflow. And at the end, the output would be training and testing TensorFlow records from this workflow.
Yeah, let me hop to the next slide. It might be, yeah, this is what we want to talk about. It's sort of unbelievable that within like 5 lines of code, you could essentially tack on as many regions as you want, and really enable through just a few lines of code what used to take a lot of effort, which was all just like pre-processing stuff to get to the model. So our hope is that this is going to make things a lot easier. It's just another thing to learn, but hopefully it'll be easier. Okay, so we're going to go into one example here now. So in the code itself, we'll hop over to that notebook just to maybe keep it even. So let's see here. Go to the very top. So for everyone who's following along, if the first thing is installing Apache Beam. Hopefully that's relatively easy. Okay, then you're going to be importing all of these different builds essentially. So we've got Beam, EE, etc., doing some Folium, blah 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 blah, putting all those versions in. Great. Now this is where we may run into some stumbling blocks for everybody. So this is where you're going to have to add. Let me switch over to this example actually. This is where you're going to have to add a project. So we have this Severe EE project. I don't know if we've got a lot of credits in there or not. So you don't necessarily have to run this, but this would be for when you're building your workflow for any model. You'd have to have a project established in your Google Cloud console. So it's a lot of like, you're going to move a couple steps forward, but then you have to, make this project in the back end in your console for it to run. But we're just testing things now, so you can explore with this. So you develop your project, and you essentially authenticate, and this is where we get into actually declaring some of the variables. So we probably spent, I don't know how much time, Biplov, sort of understanding sort of what is being laid out here by Nick's example. So it kind of makes sense for the next set of steps. But the key thing here is essentially there's these different regions that are pulled in as training locations. And let me switch back to the slides here. That these are those essentially, right? So we've got these training zones. Let me switch back again. And then there's all of these different predefined variables for points per class, the validation ratio, which is used much later on in the code itself. So it's just one block in here that sort of lays out your individual variables. And again, if you're using a different model, your training data that's going into it is going to be vastly different. But for this case, like this is the kind of thing you need to sort of pay attention to, especially sort of around patch sizes. Trying to think if there's anything that's really critical here that we don't want to gloss over, Biplov.
No, I think it's pretty simple up to there.
Yeah, and the one thing I will also mention is like the points that are being generated to create these patches later on are all based off of these initial points that are laid out here as the coordinates right here. Okay, so let's move on. So then this code, this Colab notebook. Oh, and I just saw that Deepak joined. Let me share this Colab notebook with you. Using dynamic world as another class. So I think it's grabbing Sentinel-2 and it's using like a cloudless thresholding approach. So using the cloudless Sentinel-2 probability and Sentinel-2, and it's getting rid of all the clouds. And then it's also tacking on dynamic world as a categorical variable in addition to all of the different bands. And that's what's being fed in for the patch itself. So just for like reference on what's the data that's being used, and maybe this is your first time using dynamic world, they're using this as an additional feature that's going to be, you know, tacked onto this tensor essentially. And we haven't actually used any of the dynamic world in the past. So this might be something also interesting to explore using this sort of pre-built classified image. Okay, so then here's just more information on dynamic world. You can just go ahead and run this. It's just, this is centered in like lower Vietnam. This is that one, let me switch back to this example here. So these are the training locations, and then there's one location further down in like lower Vietnam where it's actually doing the model extrapolation too. And that is what's presented in that folium right here. So I can zoom out and maybe make it a little clearer. Oh, just zoom back in. Right down here. As I mentioned before, it's just grabbing, this is all prep before we go to Apache Beam, which might be helpful for just getting us to where we need to like apply this parallelization of Apache Beam. But it's grabbing the cloud probability and the Sentinel-2 harmonized. If you haven't used this S2 cloud probability, this is something that we had just started to explore. It's maybe another little trick to add to some of the other workflows that you've got. It's a pre-processed image collection using the cloud to sen or sen to cloud modeling approach. It's listed in the documentation on the image collection for this image collection itself. But essentially, it's a collection that has all of the probabilities for clouds. So your masking could essentially run a lot faster as opposed to some QA bit masking approach. I don't know if it's better. It's just what they're using here. So if you're looking for, maybe this is most relevant in like the Amazon, if you're looking for a better cloud mask, maybe sample from this code base a little bit here. And then, yeah, it's just grabbing that cloud-free harmonized Sentinel-2. And then let's see here. It's also adding this ESA world cover map here. I don't think this is actually being tagged onto any of the bands. I think they're just demonstrating it. Okay, So now we're finally into like the meat of what we're talking about here. So there are several functions that are happening within this. There's like 3 or 4 code blocks that are actually really relevant to this discussion about getting everything into this pipeline. And this first function here is sample random points. And let me switch back to the slides. So that way, hopefully everyone sort of run until we're at this point right here, where we're at this function sample random points. Let me switch back to the slides. So we've got these regions, and then this region, for example, we're just going to focus on this one region. So back to that color example here, it's just this region right here. So think about it as like stepwise. We've got this first region right here, and then let's zoom forward. So then it's going to actually do a stratified sampling approach. So we've pulled out those excerpts from the collab to make it a little bit easier to sort of think about each of the steps. So what's yielded out of this is essentially an iterable list of coordinates that are stratified. So it's distributing a number of points that you give it by the number of classes. So if you've got, you want to do 1,000 points and it's got 9 classes for your dynamic world, it's going to give you like 9,000 points for your region, for that given region. And that's how it's actually distributing those. And that comes out as a list that you're going to use later on in Apache Beam. And Biplov, any more thoughts on some key takeaways from how this functionality is working here?
Yeah, so this is basically the usual function that we've been using. Before we used to probably provide it, the output would be a feature collection, but this time it's iterable. So you'll see that how this has been used when we look at the beam, but it's basically giving you a iterable that you can use to use, for example, a for loop to go through those list of points.
Yeah, that's key. I think the way in which we used to do it was, as you mentioned, is that feature collection. And you may have to do all regions at the exact same time. It's a huge processing job to then compile everything into one feature collection for all of your regions, which was kind of a heavy lift already. So that's the big component here. And then I wanted to put a plug in. I know we're just using this pre-baked collab, but the one factor here that you have to add in is your points per region. And there's sort of this driving science question based off of what you're interested in. Like if it's agriculture, you're doing crop type work, or if it's trying to detect, forest degradation, like what the specificity of your question is and how you have to tune that for, the number of points that you're looking at or your region of interest. Those are still things that really need to be sort of tailored. So if you're going to use this right off the shelf, just know that like it's just a standard collab. So you really have to spend a lot of time sort of figuring that out. And probably an FCNN isn't really what you want to use to begin with. So that all that's going to change anyways. But this is where I think from like the deep thinking from a science side is going to have to spend a lot of time really sort of understanding those dynamics of what you're wanting to investigate to make sure that when you're sampling all the things that you want to be sampling, you're creating that robust data set that's creating those patches for the model that you're interested in. So this part is actually going to, if you're going to use this, it's going to eat up about 90% of your time, in my opinion. Okay, so then the next thing is creating these patches. And that is a little hard to see, but essentially there is this, let's see here if I move forward. Okay, yeah, so there are a couple more code blocks right after that. And the way this collab is written, it's a little bit, you go down the, you go down through the code block and a function is happening below and then it happens back up the top, like it acts back on top. So we wanted to break this out to be a little bit more clear. Let me go over to the collab to further explain this. So we've got this first function, which is providing your stratified random samples. Then there's a next function after this called get patch. But get patch is actually used down here. So this first, we should really interrogate this one first. So git training patch. And let's go back to the slides that has a little bit more description on it. So git training patch, the thing you get out of that is the actual patch itself, which is an image region bands. And we've got here, let's see here, git patch. We wanted to show this other example, how they kind of work off of each other. And the big output, you should think about this as from your patch itself, you've got your distributed points. It's going and grabbing those coordinates. It's creating an image. It's pulling all the information you actually want from it. And then after that training patch is done, it goes to git patch and it produces a final NumPy array. So that's the output of it. And it also pickles that NumPy array. So you've essentially taken your data, which used to be, an image with all these bands, and you've distributed your points, and then you've taken that information, turned it into your patches as needed, and then you've converted that data into a NumPy array, which you can manipulate much easier and get ready for the next steps. So it does a lot of that handling and sort of leaves the image space and gets into data space a little bit easier. Biplov, any more thoughts on or specificity on this as well?
Yeah, so if you look at the get training paths, the first argument to that is a coordinate, right? So this would be one of your sample point that we generated before. If you remember from our previous function, it was a for loop that was yielding those coordinates one at a time. So that coordinate would go into that as a first argument to the get training paths function. And then if you look at where the actual patches are generating in the second function, we're using the get download URL.
Yeah.
So the get download URL had some limitation that I think, its maximum request size is 32 megabyte, and the maximum grid dimension is 10,000. You can download data either in a GOT format where your download limit would be 32 MB, or a NumPy array where your limitation would be 10,000 grid dimension. So that function has been used in the get patch function. Can you go back?
Yeah, right here.
Yeah, and also if you noticed on the get patch there is this decorator retry. So that would retry your function if there is some sort of network error or there is a network issue. It will keep on trying. So this is also very helpful if you are, especially when you are operationalizing it. So you sort of expect to have, if you have a less stable internet, then probably that function is your saver.
Yeah, and I think the really interesting thing here is this get download URL, because it's essentially creating those image chips and it's allowing that all to happen in the background. So I think we used to do a lot of processing where we're making composites, we're scaling things, we're getting the data ready, and then that data is converted into a TensorFlow record and then moved over to the AI platform. But in this sense, it's building a lot of functionality where you just do this image chipping, essentially. It's creating these very small manageable chips as a URL, and the handling between Google Earth Engine over to the AI platform makes it in a state where it can actually grab those very quickly and very efficiently, and it stages them all, it seems. So if we do this right, I think that's one area where we could gain a lot of speed back. And I'll just zoom forward here to we were kind of reading into the documentation. There's a lot of different formats that this comes in. NumPy array seems to make the most sense for, when we're getting staged for serialization, but one could argue that you could also find more uses for this geotiff as well as you're, sort of exploring how you want to chip the data. So just wanted to make a plug here that this is kind of a unique thing. And I think it's really important for the handling from Earth Engine over to the AI platform or Vertex AI. But there might be some more things we want to explore here. And when you run this code block, so everyone feel free to, if you're following along in the collab, to just kind of keep clicking along and we'll go into more detail in each of the sections. But you can see here, when you actually run this first example, it's kind of hard to read, but it's the patch equals get training, and it's actually grabbing those coordinates. It's actually running, it's using those functions, plugging in the information you want, and actually running them. It's a little bit further down in the code block. You can see the output of those. It's the individual patches and the size of them. That's kind of hard to read. I apologize. It's 128 by 128. And it gives you the different bands. So you can start to monitor, all right, how many bands are you slapping onto this? So that it gets ready for your final compression of your tensor, essentially. And you can see here that the dynamic world is a categorical variable here. And that's all handled just within this code block. So this could be a good way to sort of take a temperature of what you're developing as your patches ready for your model. So this is, I think, a really efficient way to sort of monitor that. Okay, and then serialization. So let me hop back over to the code as well, so that way we can see where we're at in it. Okay, so this code block really covers the sampling, creating your stratified samples, prepping your patches, generating your patches with those URLs, and then down here, there's one area. If you've got this collab fresh, from the link we provided, you're going to have to add in this because their example didn't have this variable defined. So you're going to have to define the points per region. I just said 1, and this is another area kind of around the big science question. It's really how many points you want to generate within your region. Then that leads to how many points per class for your strata that you're then going to sample and then iterate on. So right now, if we're putting 1 point out, it's going to actually generate 9 points for each of the strata of dynamic world. So then it's going to run the get patch 9 times and then generate that URL 9 times for that given patch. And then it's for all of the patches themselves. So back to that question, really understanding how many points are relevant for what you're looking at and the size of your region is something to explore. So again, you can just go ahead and run this once you add that code block in, and you're caught up basically to where we were talking about before of the different patch shapes and the bands and really the data type of each of those bands that are generated from each of those patches. So then, let's see here. The next code block is really just sort of viewing some of those chips that you've just created. So this code block is sort of irrelevant to the run. It's just nice to sort of explore what you've actually done visually. And you can see here that this is your Sentinel-2 chip, and you've got examples of some of the bands associated with that. And then the next example here is actually taking the classification band right here, this last band. Let me zoom over if I can. It's taking this band and it's applying a color scheme to it. And now you've got this example here of dynamic worlds information that's already attached to that chip, and it's putting that on the landscape as well. So again, it's just maybe another helpful block to sort of investigate how you're patching everything. Okay, now we're into serialization. So this is sort of a process that I think back in 2019 we worked through with Nick to create this serialization. I mean, he had already done it all, but we sort of got our understanding of how you create the binary serialization that's needed to go into Keras, the TensorFlow model, the TensorFlow platform. And that's the thing that I think we struggled a lot with of, all right, so we've got these images, how do we get further and further down to where we're just got this binary state and all the information is retained? And this is what's happening right here in the serialization. It's taking that NumPy array that you've generated from your Git patches. It took all those images that from the Git URL, and then it turned those into NumPy arrays, and then it's taking these patches and it's using this serialize to string function here. And that's what's coming out as the final product. And you can see here what it's printing is essentially a file, a string that's this many bytes long. So all of that information is compressed into this string, which is ready to go and be packaged up as a TensorFlow record. And let me switch back to the slides here because I think we talk a little bit more about that. Yeah, Biplov, any more thoughts before we go into the sort of a visual representation on serialization?
No, I think you covered it all. Just
Yeah.
yeah.
Okay, good. Okay, sorry, I didn't mean to step on you. So we made a visual representation here to sort of trace back from where we started. So we've got this patch, this region, and this is being sampled at every pixel, and a point. Let me add that point here. A point is being added, and that's creating this patch 128 by 128. Those bands here are those 13 bands. And then in this next step here, we've got this NumPy array, and that serialization is happening as we just talked about. So you're basically coming with this huge stack of data, which makes it flat with this NumPy array, and then it turns into this binary string essentially, like 85,000 bytes long or big. So in a sense, it's kind of, I'll speak for myself, it's sort of difficult to imagine how you get from the optical aspects of an image and like the probabilities that are eventually classified into dynamic world into a string that retains all this information. But if you kind of trace it this way, I think it can make a lot of sense as to how the position of all of this information still is retained as it goes into the TensorFlow platform itself. And I think we might want to come back to this for questions as people are maybe sort of running through it and going, all right, how are we making this leap of faith? Let's move on to the next one. And then in the code block right after that, we're going to get into the Apache Beam itself. But you can see here this final step as you're moving through, you've created your serial patches essentially that are, all the information is retained down into these bytes. Now we're going to split this information. So it's doing your prep work also to do 80 and 20 for your different splits. And that validation ratio is actually one of the first defined variables at the very top. So you can manipulate that as needed. And this produces like basically 2 records that are going to be used as your TensorFlow records. So it does your partition right then and there. So that's very nice because that allows you to build that functionality in, and you'd have to make sure that that's set when you go to run all of your Apache Beam. Okay, so now we're going to zoom out and actually talk about how the Apache Beam runs through all of those. So let's go over to the code block again. So over here, we've got, if we zoom down to the next one, right here. So this is where you're splitting the data like I just mentioned. And you can definitely go look into the Apache Beam for more examples. So like this pipeline options, there's a lot of description in there that is probably worth exploring. We just barely sort of started scratching the surface, and we started to look at some of the functionality here in create, and flat map, map, and partition. It's pretty straightforward if you look through the documentation itself, but you can see here there's these 5 distinct steps that we just talked about: regions, sample points, get patch, serialization, and data split. And this is where it's actually starting to run through each one of those regions, through all of those steps, and it just is basically creating a giant processing system for you. And the final output of this, again, is these TensorFlow records for each of those splits. So within here, this is where all of those steps map back to. Biplov, do you have any additional comments on this too?
Yeah, so the pipeline that we're using, it's an abstractor. It encapsulates your entire data processing tasks from start to finish. That includes like reading your input data or transforming those data and writing the output file. Each of the function, for example, the beam dot create or beam dot flat map, is provided with an argument from above. So if you are looking at the sample random points, the beam dot flat map, the first argument that goes into that function is one of the reason. So it takes one reason, produce those sample points produce the paths, serialize them, and then split the data. It does that process for all the other sample points out there. Um, so you have this end-to-end pipeline abstraction written in that 5 line of code. You also uh, have activated the parallelization, or if you look at the beam option, you can specify the number of workers that you want to run. So in this case, we're running each of our processing for each of the region in a separate worker. So that's why we have specified our number of worker as a length of region, so that each of these region are running parallelly. Yeah, so all those steps that we saw focusing on one region, now it's been scaled up to the entire training regions that we saw earlier.
Yeah, and that's why I think it's really important to sort of get a full handle on each of these functions that are defined above, because it's cascading those as you move through. So one thing I'm glad you brought this up, Biplov, is this number of workers. Obviously, it's tied directly to your total number of regions that were defined up above. I think there's like 5 regions, but this could be something also to explore if they're, depending on how fast you want something to run, what's the level of effort that you actually want it to produce. This is another area that you may want to also explore as well. This is, again, just the existing example here. So I think all of us maybe collectively want to start exploring this Apache Beam. And if there's something else that we can tweak, it's a little bit more efficient for us, or especially for cloud optimization around the world too. I think the question I have in my mind is there a more cost-effective way to do this also? Yeah, I think let's just sort of wrap up our slides to leave us some time for questions as well. So again, on the very high level, you have all these regions, and it's moving through each of these steps as it's going across, creating these individual splits, and that preps everything for the model. So we've really only made it halfway through this notebook, but you've done all of the work that you would need for your patches that are now serialized and then converted into TensorFlow records. So you're ready to just run your model. So you have to really interlink what model you're going to use versus this pre-pipeline. So if you're going to use a UNet, or if you're going to use a CNN or an FCNN, the type of data that you're using, or the data shape especially, is really important. So you might have to jigger that as needed, but this process is pretty straightforward now. So you just kind of have to make sure you're connecting the pipes correctly. And then let's go to this next one. Yeah, so I know we sort of did a really fast dive on our impressions of the Apache pipeline, and